coming thanks to WASP. And the first presentation comes from Carl Sager from Chalmers.
Thank you. So let me start with once upon a time, there was a designer. Design engineers that got tasked to do interesting problem. He has to design a little small piece of the chip that implemented an algorithm that was tricky because it has to be iterative. He couldn't just build a combinational that was way too, it could be way too big. So he went to the literature and did a lot of research and so on and so forth. And of course, like everything in the microprocessors, you want it to be really fast. So he came up with an idea that you could actually cut the number of iteration in half. The only problem with this was that, well, it wasn't quite, you couldn't quite do it. Each iteration, you had to sort of only get an approximate answer. And the approximation was sort of rough. So it wasn't quite clear whether it was going to work. However, if you were clever about the choice you made, it turned out that, okay, you got an approximation, and if you as long as you made sure you made the right choice, you could actually recover if you made it slightly wrong. So effectively, you stayed within error bound. You did the approximation, you went ahead and ran it. That worked just fine, except that you needed a fairly large table to look up to decide, okay, which decision should I make? So they put a table in, and he looked at it and said, gee, that's big. But then he realized, oh, well, look at this. This is a beautiful table. It's symmetric. We can cut the table in half. We just need to store half the table. Well, almost. There is one or two entries in there that doesn't make it quite symmetric. But you know what? That probably doesn't matter. Well, actually, he tried more and more, looked at various simulations and analysis, and convinced himself that, no, that can never happen. Unfortunately, he was wrong. This is the famous Pentium FDiv problem from 1994, that Intel had a divider that was almost correct, but it was correct only 99.999998888% of the time. Intel claimed, of course, that if you used the machine, you would see this once every 5 to 10 years, which is about the age of a computer. IBM disagreed and said, well, if I run a big spreadsheet, it's going to happen about once a day. End result was that Intel, of course, had to recall all the Pentiums to a cost of about $475 million, which is today would be about $750 million. A lot of money. End result of that was, of course, that Intel said, this cannot happen again. We need correctness, absolute correctness, no question about it. So as a footnote of this was I ended up in Intel. I spent 1/3 of my career in academia and 2/3 in the industry. And I wasn't planning on being in industry, but I ended up there for quite a while. However, we ended up taking academic research and that I had been doing and others had been doing, and we drove it into deployment. Not just develop new technology along the way, which we obviously had to do, but we also drove it into methodology and design. So any of you sitting here using a computer, I can guarantee you that most of them have an Intel chip in them. AMD does not. They do analysis, but not using our tools. But the Intel chip will have part of this chip completely verified using those tools, which is kind of fun to see. I like the fact that we haven't seen anyone. Now the nice part was I was able to retire early before we discovered they had missed some bug. That's important. You have to make sure you're gone before the damage shows up. However, so what I'm doing now is I'm focusing on, obviously, correct, robust, and secure systems. But then I started looking at machine learning stuff, because after all, this is a hot topic. So since I now have the freedom to look at things for fun, rather than just what immediately is important for the company, I realized that the quality of solutions is usually measured fairly statistically. You do test cases and say, okay, we got 90% coverage, or we got 99% correctness. That didn't feel very well to me. It didn't sit very well. So remember, the FDiv was really, really good. It was just not good enough. I'm afraid that I feel that there are some, in particular, safety-critical things that I would like to have guarantees. I would like to have some sense of seeing, yeah, that algorithm is guaranteed to be within the specification. In other words, it needs to be specifications, among other things, before we even go any further. So, in particular, you must return something in certain cases, and you should never return certain things. If you think about traffic signs, I would like to say that if you see a 70 sign, you should return a 70 sign. I don't want it to return a 110 sign when you are in a school zone, for instance. They should never do that. Very mundane and very simplistic view like it. When I started looking at this, I also discovered that, well, I thought about it for a while, and I said, well, there are certain types of problems that seem amenable to this. And that's what I call one-way problems. They're sort of two different parts of the same problem. Like think of, it's very hard to recognize an object in the picture. But it's not that hard to actually draw a picture. All our video games are amazingly good on drawing images. In fact, Mark's talk from NVIDIA yesterday had showed that they use actually computer-generated images for training material. So it's actually a lot easier to draw than recognize. So this duality was sort of like, can we take advantage of the technology that we have developed in the formal verification world for doing those kind of things? And I think there's an interesting possibility here. So what we're going to do is describe an object in a language with symbolic variables. So we're essentially going to, instead of drawing a single image, we're going to draw a family of images, a very large family. And then we're going to use that to sort of, as a specification, then we're going to try to verify whether things work. And if you know me and my background, you will also know that lattices will show up somewhere. And in fact, abstractions are incredibly important in formal verification, and we will use it in here as well. So we'll combine the symbolic techniques with lattice structures. So to give you an idea, I have built a system called WASP2. 2 after number 1, that was ended up being the system that ended up going into Intel. And unfortunately, when I retired, they didn't allow me to take the system with me, so I had to start from scratch. So this is number 2. Just to give you an example, here's the collets, little function. It's a functional language. So it's a function that computes how long is a collet sequence for a particular number. If you don't know what the collet sequence is, it's the famous conjecture about if you take an arbitrary number, an integer, let's say 3. If the number is odd, you multiply by 3 and add 1. So 3 times 3 plus, that's 9 plus 1, 10. If it's even, you divide by 2. It's 5. 5 times 3 is 15 plus 1, 16. 8, 4, 2, 1. You get about 1. And if I count right, it's 8 digits in that sequence. The big conjecture is always, it claimed that you will always end up at 1. I can't tell you whether the answer is that or not. I'm not even remotely good enough mathematician, but as far as I can tell, there's no one else yet either. However, I can write a little function here that does exactly this. It just computes it. And not surprising, if you compute it for 3, you get 8, and you do 7, you get 17. However, the interesting thing in this system is that you can also, instead of giving scalar values, you can also give symbolic variables. So here we're going to give something a bit more complicated. We're going to say, well, it's an arbitrary variable, but it's bounded between 1 and 50. In other words, in one shot, I want to symbolically, or if you think algebraically, compute all the answers for the Collatz conjecture for any value between 1 and 50. And if you apply that in, we get some answer. Instead of an integer, as a result, we get an expression, which, of course, if you look at it, you say, not very useful. However, you can ask interesting questions to it. You can say, OK, give me the condition, and the result is at least 150. In other words, there's at least 150 elements in the sequence. And it comes back and says, false. Oop, there is none. Within the first 50, there is no sequence of 150. What about 100? Greater than 100? Well, actually, it turns out that there is some condition for which that is true. It's still kind of hard to see anything of that. After a while, you can stare at it for a while, and you might be able to figure it out. But you say, OK, just compute some examples of it. If it turns out that I gave it compute 10 examples, and it only returns 4, it turns out that means that there only are 4 examples. So 27, 31, and 41, and 47 all have sequences longer than 100. So it's kind of a cute thing to do. How does this relate to autonomous vehicles and things like that? Well, take a more interesting example. Let's do a scalar algorithm to symbolic. Bresenheim's circle drawing algorithm is an example. Here's this, the imperative version, and here's the functional version, effectively transliteration. But of course, now we're using it with symbolic variables as well. Scalar, as before, you get a circle. Circle in the center at 16, 16. Symbolic, now we do x-coordinate symbolic. And here's all the possible values you can get. And here's a couple of examples from it. So I generated a whole bunch of them. By what actually got computed is one expression for all of these entries. And here I just did random samples from there. If you use symbolic radius, it looks like a torus, not surprising. You get the random examples. And if you do the whole thing symbolic, you get a little bit over 2,000 images effectively captured in one expression. Now, so what? We can just run a program that generates 2,380 different images. Yes, we can, until we do something more complicated. Here we draw an ellipse, a circle, and a line. And actually, it turns out we effectively generate 274 billion versions of those in this graph. Here I gave you 12. Clearly, you can actually very quickly now capture a very large number of images. So as an example using this, let's look at street sign recognition. Very simplistic. It's a hard problem in general. So here I'm going to give you a very, very brief and very sort of first version or child's version of doing this in this setting. The first thing we would do in general would be an abstraction. So here we filtered for just red circles. We actually filtered for red. And with pretty wide red. So we kept only the red. I drew the image afterwards just so you can see what happens with the abstraction. Normally, of course, you don't draw it again, but you just do it on the fly. You then try to find a red circle. And if you do the computation of a camera sitting in a car seeing a street sign between 10 meters away or 5 meters away and 50 meters away, and you do the geometry, a little high school geometry, and you see that the size of the circle is bounded from here to here. And you say, OK, find all those images wherever on this 1280 by 960, there should be a circle or multiple circles at that size. And here's 8 examples of the 55 million circles we're actually looking for. And once you get the location of one, then you can take it and extract that piece. It's more detailed. Then you now can take the same idea. Now, instead of drawing a circle and drawing it, you can actually take the image and apply the same idea of symbolic variables to translate the image, to scale the image, and to rotate the image. And possibly even using symbolic variables to change the coloring schemes. Because you may want to have daylight, early morning, late night, well, not late night maybe, but late day, and so on and so forth. If you do this, you can then recognize signs. So in general, what we end up with is an example where we get symbolic expression as a specification, if you like. We now have completely covered and be able to specify exactly what images should you recognize as a 70 sign. No matter where it sits on there, whatever you want to say should be satisfied. So you can use this spec now for a number of different things. Well, first of all, you can clearly use it to generate data for your machine learning techniques if you want to use that. The nice part here, because it's symbolic and has expression, you can actually fairly easily say, oh, I want to get corner cases. I want to do things that are certain things. Like early morning lights, or when they are rotated as much as you can allow. All the things you probably would be very hard-pressed to get if you actually went now, drove around and looked for things. So it's fairly easy to generate boundary cases, which is useful. You can also take it, if I'm not coming from an FE background, you take this and take a trained network and say, OK, now I can take the spec and I can actually simulate it symbolically through that network and get an answer for how good is it. I mean, in reality is that it's almost guaranteed to come back and says it's going to fail. The question is, how often does it fail? You can actually have an objective metric on how good your training turned out to be, as opposed to just statistical. On the other things, you can also use, conceivably use this for better training. And I think the most intriguing one is maybe the last one. So if I simply say, forget about machine learning here. Just simply say, well, this is a symbolic expression. Why don't we just use a SAT solver and an online SAT solver here to actually determine whether there is a match on this or not? You could very well imagine building essentially a SAT-based solver here that sees the images coming in and just determine, is there a solution to this matching problem? And if it comes back and says yes, then you have everything ready for you. And I think that's the end of my presentation. Questions?
Fantastic timing.
you using SAP solvers?
Yeah, I'm using both SAT solvers and BDDs and SMT solvers. I use everything in the system is all built in. Yeah.
Regarding your last suggestion, have you compared this to similar approaches where the geometric transformations are done by invariance principles, for instance, based on Fourier descriptors?
I've looked at a little bit of it, and I'm too early to tell you whether this works better or not. Part of the problem with that one is it's hard to tell what you're actually specifying. Part of the reason here is I would like to have a correctness specification. Now, the interesting thing here is, of course, I have a spec. Now the question is that the spec correct? Effectively, you actually have to evaluate the spec quality before you say anything else. In fact, a lot of things I discovered when I tried to use it was that, oops, the spec was a little bit too strict. And maybe there are things. So for example, the camera, you think of the camera as an RGB, you just generate the numbers. But of course, real cameras, cheap cameras that cars have, don't have 3 sensors for each pixel. They have 1 pixel with 3 or 4 different colors and then use interpolation between them to generate the right. So edges in particular are not what they should be. So you get problems from that. You get problems from the compression that all these images have gone through. They are not lossless. So these things now have to be moved into the spec, maybe. At least currently, I'm moving them back into the spec. The spec actually has to incorporate the fact that there are losses. There are incomplete, incorrect pixels. Pixels are dead in the image and so on and so forth. So all of this has to be captured in there. But none of this is hard in the sense that, yes, you have to put them into the spec, but they're fairly systematic ways of doing it.
Okay. Thank you very much.
Thank you.
Okay. And second presentation of the day of our new faculty, Christopher Zack. Yes.
Okay, hello there. Is it working? Is the microphone working? Okay. Okay, hello everyone. So thank you for still staying around. So I think my presentation will be slightly different to the previous one. So there will be equations eventually showing up. I hope to keep the time going through this to a minimum. But first, a little bit about my background. So I actually did a PhD with a topic in 3D computer vision. So more or less, the task is you have a set of images or a video and you want to create a 3D model. Like, for example, first, usually go you via sparse point cloud, what we call it, and then you try to obtain some dense reconstruction you can visualize or in some ways analyze, and you have applications such as localization that is very important these days as well. I also leaped into neighboring fields, so I worked at some point with people doing medical image analysis and also with computer graphics people that worked on free viewpoint video. One of my passions is writing down things as, let's say, energy objective and looking at the problem from the perspective of mathematical minimization. Just a few pointers or a few details about myself. So I did my PhD and also my undergrad at TU Graz, which is in Austria, and it's probably still a quite well-known place for computer vision research. I had various stops in other places, and recently I was at Toshiba Research Europe, which is located in Cambridge, UK, and in October 2018, I came to Gothenburg and joined Chalmers. So for the statistics, so one successful recruitment, so a postdoc who will start soon, and hopefully a PhD student will start in later this year, and one further announcement for a position should be out anytime soon. So actually, this WASP package I got is a big opportunity to move away a bit from computer vision, which is my original research topic, to something that's maybe more a passion, is kind of understanding AI and the current version of it, that's deep learning. And so one has to look at, despite all the successes you see in the media and in the research community about what deep learning can do, what are the problems with it? And yesterday and today there were numerous talks mentioning some of these problems. And at the end of the day, you can summarize it, I guess, as follows. So deep networks are very successful. But first, we don't understand them really, what's going on. And the second thing is, deep networks are not intelligent in any meaningful way we would think of them, or think of in AI terms. Meaning there's currently lots of empirical, but also emerging theoretical evidence that actually deep networks, when you train them, for example, on images to classify images, they're looking very much on superficial texture features instead of understanding what's really going on in the image. And to go into this a bit further, so I kind of elaborate on the tasks you want to solve, which is usually some prediction task. So given an input, you want to predict some output, let's say image layer. And there are two kind of modes or regimes you can operate in. The first one is the usual one, which is more like interpolating. So given training set that looks, let's say, like natural images, and you have attached layers, interpolation more or less would mean you provide new images that are also looking like natural images, and you want to obtain some output, which in this case looks fine. Then there's another regime, which I call extrapolation. So what happens if you train on this kind of data, but provide data like this, for example, random pixels, or let's say artificially generated geometric structures that have nothing to do with this kind of data. Almost all deep learning architectures that are in use today will very happily tell you kind of these type of images look very much like, let's say, there's a cat in these images. Do you see somewhere a cat? The network says yes, of course, we humans are very clear about that. These are random pixels and have no particular meaning. But deep learning, as it is today, is mostly completely ignorant to this problem. Just to summarize again, so taking a picture, in this case of Taj Mahal, so let's say you have a network that does location recognition. There are two modes, or two failure cases. One is you add a bit of noise, and then the system suddenly does not recognize it as Taj Mahal anymore, although it's clearly clear for humans that it's still the same thing you see. But on the other hand, very random pixels, it is very confident in telling you this is what I see here is Taj Mahal, which makes no sense. And so lots of research goes into this topic. So recently, it's called adversarial attacks. I think much less is concerned about this, but I think I'm going to talk a bit more about that one. These things are, of course, relevant, not just because you can say if I get an image layer wrong, it's not of a major importance. It's more an annoyance. But for example, and this setting was brought up, I think, already yesterday, if you misclassify traffic signs, that can have very serious consequences. And these adversarial examples, they all come back to what's really, or one thing that's happening with deep networks is instead of using a very regular, very nicely defined decision boundary like you get with linear classifiers or SVMs, you have a very complicated, difficult to describe decision boundaries, which means, especially in high-dimensional spaces, a lot of your data points will be close to the decision boundary, so it's very easy to cross the boundary. And another setting that kind of I encountered personally at Toshiba Research, where I was before, is you train a network that does what we call semantic image segmentation, and there are very good networks to do this. For example, you take an image like this, you get a very nice output like the following. So you have very nice segmentation or classification of the different parts of the image in the different semantic categories that are indicated by color here. But if you apply these networks that are very good in benchmarks on possibly more realistic data, like a heavy rain scenario, you get a segmentation result like this, which is totally useless. And one of the problems is the network is not telling you that this is totally useless. So one thing is predicting something correctly. The other thing is, if you're unsure about the prediction, you should, let's say, notify the system or the user in some way, which is unfortunately not happening. And so one sort of line I have in kind of this regard is the following. If you train a network on natural images like this, and you get this kind of Gabor-like filters, these are the first level features you are supposed to see or supposed to get when you train networks with sufficiently large data sets, then it should tell you something about how these original images looked like. And it should tell you that these kind of images were not part of your training set. And so, going back is, so what you want to extract from this kind of information you get from a trained network is some idea of confidence when you plug in a data point. Is the network confident about its prediction or not? But there are different notions of confidence. Some, at least here and there, are unfortunately easy to confuse, and also, I would say, not fully correctly used in the literature. So there's one notion of confidence which is very often used, is just sensitivity of the learned weights with respect to your training data. This then leads to these Bayesian networks and so on, which are recently somewhat popular. The other one is, which is often used, is the sensitivity of your prediction on your input. And this is what very often is considered as confidence, but this only tells you, in a way, if you change the input slightly, would the output change as well? So it's more about sensitivity analysis. It's not about confidence that the network is classifying something that it has seen beforehand. Sometimes when you look at Gaussian processes, these formalisms can be converted into each other, but this is not the case for neural networks. And one possible approach to assign some value of confidence to inputs given a trained network could be energy-based model, which I will just summarize briefly on the next few slides. So the idea is for an input, let's say input pair output target, you and given weights, you assign some scalar energy value that kind of tells you how likely, in a way, this input pair is according to the weight. And it should be, let's say, a smaller value, let's say close to 0, if it's very likely, and higher values if it's very unlikely. So this justifies using the term energy in this case. What you can do is, for example, using an energy model, you can give an input, predict the output via solving some minimization problems. So you replace the typical feed-forward architecture by minimizing over variables. You can assign, like, what you call it, posterior, but also very important, you can assign something like evidence, which is more or less connected to this minimal energy. Okay. And what it turns out is, if you look at a standard feed-forward network, let's say with Velo units, you can assign a very simple energy model to it that behaves very similar or as close as you want to this feed-forward network. And the energy looks like this. It's basically just square terms. And because, let's say in our case, we say we want a rail network, you have some non-negativity constraints of these internal activations, which also show up in this energy as extra variables. The prediction task, again, is solving some minimization problem. What you also have is what we call the feedback weight. So how much the next layer affects the computation of the current layer. And if this feedback weight goes to 0, what you obtain is the behavior of a standard feed-forward network. So why is this interesting? So there are several reasons. So the original papers proposing similar the energies or concepts like this, they were talking about the fact that once, or you can do better with, or in some ways better with training a network, because once you have fixed or determined these internal variables of the network, the training program decouples layer-wise. So it's not everything is connected anymore like you would have in backprobe, but you decouple the problem of learning into a layer-wise problem. So and which is also meaning that, for example, you can add more parallelism. For me, one of the interesting aspects is you have a simple and somewhat interpretable and also convex kind of energy assigned to what the computation is within the network, which, for example, has then implications on to do formal verification of deep neural networks and also data imputation. So, for example, if you have an energy like this, which is convex and very nicely behaved, you can, for example, given y, you can also compute what is the most likely in terms of the energy input x for a given target output y. Or you can mask out parts of the input and compute the remaining elements. There are also things what turned out is this model leads to slightly more biologically plausible approaches. And so I think which is an interesting point. And another interesting point is this can be seen as another tool to maybe interpret or trying to understand deep neural networks. Okay, training, to skip things here a bit, it turns out that if you train it the right way, it's actually in the limit the same as backpropagation, which kind of is I would say, formal justification of looking at this kind of energy-based models in this context. We can, yes. And the other thing is, yes, you can now take new data and compute the induced energy. And what it turns out is, if the network is behaving more linearly for this input, then the energy is lower, meaning for this network it looks more likely data, which is kind of interesting because of lots of methods that try to improve the learning of networks. They're trying to make the network look more linear for the training set, meaning, for example, batch normalization is exactly doing this. If the activations are very sparse, then the energy is high in this energy, and this data does not look very likely. Which is also sensible because very few neurons or units will be active, so meaning this is something where very little computation is actually happening. You can apply this on some, let's say, toy data, MNIST, so the problem is to classify digits that are given as black and white images. And if you run these things on test data, so the average energy is the lowest. If you run it on data that you corrupt, for example, by adding digits or flipping the digits, so doing a left-right mirroring, then the energy goes up. If you provide kind of some Gaussian fit, independent per pixel, then the energy is even higher. And if you provide some kind of non-digits, meaning some symbols that come from other, let's say, writing systems, then the energy is also a bit higher. So there is a trend that looks interesting. So the caveat is that these are average numbers. And you see on the top row, you see the kind of the least energy, or the most likely example, and this is the less likely example according to these data sets. The problem is the variance of these energies within these data sets is quite high, so you have quite overlapping distributions, although the trend is kind of doing the right thing. You have overlapping distributions, which is some problem to address in the future. And I think the last slide is, it came from 3D computer vision, and yesterday there was this claim computer vision is solved, and I have to publicly disagree with the statements. So there are still, even in 3D computer vision, there are a lot of scenarios like transparency, reflective surfaces, etc., where current methods in computer vision completely fail, and we have very little idea what to do there. So with that message, I conclude my presentation. Thank you.
Thank you. Okay, just one very short question with very short answer. it's extremely short question and answer, so it's no question, no answer. So thank you very much.